Welcome to this on Observational and Theoretical Astronomy. It is jointly organized by Astronomy Club of St. Xavier's College, Ahmedabad, Department of Physics and Electronics, St. Xavier's College, Autonomous, Ahmedabad, and Essencetech. Today, we have the third speaker for the day. Now, and I would like to invite Dr. Tushar Pandya, sir, senior faculty from Department of Physics and Electronics, St. Xavier's College. So please introduce our today's speaker. Yes.
Thank you, Chintan. Thanks, Chintan. Good afternoon to all, my dear participants and physics educator. Today, I'm very happy to introduce my friend, Dr. Brijmohan Thakore. Dear friends, Professor Brijmohan is a professor of physics at Sardar Patel University. Basically, he is a theoretical physicist and having more than 25-year teaching experience. His area of research is a theoretical condensed matter physics. His more than 50 research papers are published in national and international peer-reviewed journals, and he has attended many national, international conferences. More than 15 students worked under his supervision and awarded MPhil extension of research work and the collaboration. He has visited International Center for Theoretical Physics at Italy. Dear friends, other than being a physicist, my friend is a well-known amateur astronomer and a resource person in astronomy and astrophysics. Astronomy is his passion. He has conducted many astronomical workshops, sky-gazing programs across our state. He has promoted and supported various science club and astronomy club of science colleges of our states. Friends, he is also associated with our astronomy club of St. Xavier's College and supported our activity and mentor our students. Professor Brijmohan, we thank you for your kind cooperations and support, and special thanks for accepting this invitation to support our activity. Friends, during the period of year 2016 to 2019, he was the honorary director of the Anand District Community Science Center, and he conducted many outreach programs and promoted science education camp as well as several programs. He appeared in multiple TV talk show and scientific debate. He is an active member of our Regional Council of IAPT. He is a fellow of Gujarat Science Academy and is involved in various activities conducted by Regional Council of IAPT as well as Gujarat Science Academy for promoting science and popularization of science. Dear friend, we are very fortunate that we have an expert with us online. With this brief introduction, I request Professor Brijmohan for his talk on observing the sky, and I'm sure you will enjoy his talk because he's an excellent speaker. So, Brijmohan sir, please, I request you for your presentation. Thank you.
Thank you, Tushar bhai. Can you hear me?
Yes, yes, please. Yes.
Okay, so thank you, Tushar bhai, St. Xavier's College Astronomy Club, and other organizer for arranging this talk. Friends, today I will be talking on the topic is observing the sky, and as I was told by the organizers, the listeners or the participants for this particular session are mostly amateur astronomers who have recently joined some astronomy club, the St. Xavier's Astronomy Club, and therefore I will keep it simple. I was told to introduce the night sky, how to observe the sky, and the concepts involved, which will help them further see the sky and enjoy the universe in a better way. So friends, I will be focusing on the three coordinate system, whatever diurnal motion of the sun, the moon, stars, as well as the annual path of the sun and moon, etc. And then later on, if we have time, I will take up some other things also. Let me first start with a small animation which will show you the Khagol or the celestial sphere. Kha means star in Sanskrit and Gol means sphere. So the Gujarati or Hindi name for astronomy is Khagol. It helps us to get an idea of what stars we can see. Now I've started this animation. If you go out in the open and face the sun direct many hours, you will find that the stars rise from the eastern horizon, take a southerly path, and then gradually go and set in the western direction. So this this is the concept of celestial sphere, where we are supposed that we have a sphere of imaginary sphere of infinite radius, and the stars are supposed to move on that sphere. Now the question is why we take the imaginary sphere of radius r and suppose that all the stars are on that sphere. The reason is, say, in the night time we see many stars, and many of them are very bright, some are not so very bright, and some are very, very faint. If you go out in the open on a highway at night time and say a truck is coming, whose headlight is very, very bright, but if that truck is very far off, you will not see that bright headlight. But if you have a vehicle like a scooter whose headlight is not very bright, but that scooter is very near to you on the highway, it may seem that the light is very, very bright. So brightness simply does not give you an idea of the distance of a star. But if you want to find out the relationship between the angular distance between the stars, which stars can be seen from your place, want to find the rise set times, etc., etc., then this concept of celestial sphere comes in very handy. So now, as you can see in this figure, this side, this is the celestial sphere, right? On this side. Okay, and this is your position. Suppose I have set this figure where this position corresponds to the latitude corresponding to somewhere in Gujarat. Now, as you can see, this is the North Pole, and here you have a star which is known as, this is on the celestial sphere, you have this North Celestial Pole where you see a star which we call Polaris. This is the South Celestial Pole, and this is the celestial equator. This is just a projection of the equator of Earth. So you are projecting the equator of Earth to an infinite distance, and that celestial sphere and the Earth sphere are concentric with the center of the Earth. Now you can see some stars, the North Cell star, you have a star here, and several other stars. I've shown some stars. If you look at the corresponding horizon diagram view here, then this is what you actually see from your place. Because if you draw a plane which is tangent to the spherical Earth from your place, then this is what you will see. The North Star now appears here. These are the four cardinal directions: the north, south, east, and west. And this celestial sphere, celestial equator is now here, starting from this and going like this. This is the equator. So this particular star which I have pointed out here, now it is appearing here. And the angle which this pole star makes here up to you, this is equal to the latitude of your place. So if you move to a different place, then the position of the pole star may go like this or this. If you move to South India, say where the latitude is only 8 degree, then the pole star will be very, very near to the horizon. And if you move up, that if you go to latitudes like 40, 50 degree north latitude, then this star will move up exactly at the pole, then this pole star will be in this particular position. So this is the comparative between the celestial sphere view and what you actually see at your place when you are trying to uh, see the stars and see the other planets, etc. Now, we can come back here to this particular diagram. This is the pole star, and any star which is in this region, those set. But if a star is away from the pole star, say this position or this position, then they will rise and set. And there is a region here which is below the horizon. So this particular animation shows you three different types of region. So this particular star is known as a circumpolar region. This is your pole star is somewhere here. So this particular star, the blue star, will never set. It is different that in the daytime you don't see the stars, but these are circumpolar. This is a circumpolar star. Next is this yellow star. It rises from the eastern horizon and sets here in the western. So for part of the path, it is above the horizon, and for part of the path, it is below the horizon. So you can see the star for many hours. And then you have this star, which is shown in green color. Horizon, and as Earth spins around its axis here, the star makes a circle around the axis, but because it is below the horizon, you will never able to see it. So which stars you can see, and they will be circumpolar, which stars you will not be able to see, and which stars rise from the east on your location and set in the west, that you can understand very well from this diagram. Now, as I said, if the latitude of your place changes, then the pole star position may shift in this direction or this direction. And then what happens? Some particular star which is not visible from your place may come above the horizon, as can be understood from the next figure. Okay, this particular animation shows you the circumpolar stars which we're talking about, this particular stars. So if you are facing north, then the region which is shown here by the dotted curve is the region in which the whatever stars are there, they will be circumpolar. This center is our pole star. This is Ursa Major. Then you have Xavier, etc. So those are the stars which will always be above the horizon. But if you look at the stars which go here, they will come up here. So for part of the orbit, they are below the horizon. So they will rise and set. But this is the circumpolar region. Now let us look at this figure. Again, I have the celestial sphere view and what you actually see from your place. So again, I have this Earth, and this is where you are, probably in Gujarat. Now, this region, this brown region, shows you the stars which will be circumpolar. And again, you can see this is the North Pole star, this one. And this you can see from your place, which is this one. So this is the North Pole star. And again, it will be at an angle which is equal to the latitude of your place, right? See this star. So it is slightly below the celestial equator. So this is the celestial equator now, and it is here, right? So this shows you which stars will be, which can be seen. Of course, now these stars, the region, in this region, whatever stars are there, you will not be able to see. Now, if you change the location, what happens? How the sky changes when you change the location? So instead of this, this is figure corresponding to latitude 22 degree. Now I change the position and go to say 40 degree latitude. So now from here you have moved up, and this is roughly 40 degree north latitude. See what has happened. You compare the two figures. These are the circumpolar stars, and this particular star is outside the circumpolar region. So it will rise and set. But when you move up from 22 degree latitude to 40 degree north latitude, now that star has come within this circumpolar region. So I will just flip that, and you can make out that this has come inside the circumpolar region. So from that, the position of the pole star, which was here 22, it goes here, it moves higher up in the sky, and this particular star is now come inside. So the number of stars or the region of circumpolar stars has increased as you move up. Same way, this region has also changed. So when you move up or down, you change your latitude from 20 to 30 to 40, then what happens? The whole sky moves in this direction. So whatever was initially visible from your place, say 22 degree latitude, the star here was visible, but now that has gone down because the whole sky moves in this direction. Even your pole star moves from 22 to 40 degree. So when the place of your observation changes, then the number of stars or which stars you can see also changes. For example, Canopus or the star Agastya is visible from Gujarat these days, but it is very low in the southern sky. All right, our latitude is around 22, 23, Nadia Anand. But if you go to a latitude, say 40 degrees, then what will happen? The southernmost star Canopus, which is visible from here, will go below the horizon, and so it will not be visible. So when you move up, the stars which are visible in the southern direction initially, now they become not visible, right? And similarly, new stars come up from here initially, which were below the horizon, they come up. With the pole star moving from here to here, the stars which were initially below the horizon now move up. So you see a new sky compared to your previous latitude. And so the sky changes with latitude. Next question is then, what is the, when the stars will be visible, at what time they will be visible. If a particular star is visible today as say 8 o'clock, it rises at 8 o'clock, then how its rise and set time will change. So for that, we need the concept of sidereal day and solar day. This can be explained with the help of this figure. Now look at this figure. This is our Earth, right? And you have the sun here. If you are standing here, then it is noon for you, sun overhead, and above the sun, very distant star is there. Then this is what you actually see. You don't see the star, you only see the sun. You don't see the sun, try to see the sun, but I'm simply talking about the position point of view. So the sun and star both are at the same position as far as your position on the earth, and with respect to that, it will be at zenith, right? Now, as the earth moves in 1 day's time, what happens? The earth is, when it moves in the orbit, it also rotates like this, and therefore when again it is in this position, you are in this position, see, this position and this position are exactly 360-degree rotation. One rotation is completed. So now what is the situation? The sun is not overhead. The sun is somewhere here, right? Okay. So again, after about say 1 degree, when this position is reached, you are here. The earth completes more than one rotation. From here to here, this is 360-degree rotation. But now you have to go 1 degree more. Then you will have sun overhead. But then when the sun is overhead, there is a displacement of the star, right? And this is what you see. Okay. So this is 24 hours day, overhead sun to overhead sun, 24 hours, right? But in between, right, the star position is this, because the stars are too far off. This position and this position of the earth correspond to when the star will be overhead, right? And therefore, something what happened. So what happens? This is from this position to this position, sun is overhead. But from this position to this position, the star is overhead, right? Therefore, this naturally requires 1 degree more here. And so if this is 24 hours from this position to this position, this is slightly less. And it is less by an amount which is roughly 4 minutes. So when the star rises, say today at 8 p.m., tomorrow the star will rise at 7:56 p.m., 4 minutes earlier. Next day, 7:52, and so on. So daily there is a change of 4 minutes in the rising time of the star. And 4 minutes daily means that it will be 2 hours in 1 month. Fine. And 2 hours in 1 month corresponds to 24 hours in 12 months. It's simply 1 month, you have difference of 2 hours. So if on 1st April, if a star is rising at say 9 p.m., 1st May, it will rise at 7 p.m., 2 hours earlier. So if there are 12 months in a year, naturally it amounts to 24. So next year, again, it will rise at the same date, same time. But daily, there is a difference of 4 minutes. Okay. So when you are trying to find out which stars are visible and at what time they will rise, naturally, you are observing the stars, the sky from your place. So you need some reference to find out the position. It rises at a particular time, that's fine. But then to find that star, you have to know in what direction to look and how much up, right? So for that, we have a altitude azimuth coordinates, and they are known as the horizon coordinates, right? So for that, this north, it corresponds to 0 degree. The azimuth and altitude are given in terms of 2 numbers. One number represents how far up you have to look, and the second number will give you how far from the north you have to look. So this north is 0 degree, east corresponds to 90 degrees, south corresponds to 108, 270, and again you come back here 360. So as far as the star in the figure is concerned, that is this particular star, see, the first number is altitude. Altitude is measured from the horizon. So it can be on the eastern side or western or whatever, but you have to find out the angle which it makes with the horizon. So this is the angle from here to here. This angle is 50.2 as far as this figure is concerned. And the azimuth you have to measure from north to east to south to west and so on. So it is shown by this yellow line. This yellow line is drawn. It shows the azimuth of this particular star. It is greater than 240. It's here 300. So this 300 is the angle which is from the north to this position, right? So these are the 2 coordinates, altitude and azimuth. If you buy a telescope, then mounts of various types are coming, and you have altazimuth mount. If you look at the specification of telescopes, then it is mentioned that it is altazimuth mount or it is equatorial mount and so on. So that altazimuth mount simply means it moves in a vertical plane and a horizontal plane. These are the horizontal coordinates. Now, this is another example which will make it clear. You are measuring from here north. So for this star, it is azimuth is 234. It is larger than 180 and between 270. So you know that it is in the southwest quadrant. And then this is the height or the angle from the horizon. If even 30, then 40, 50, 60, 70, and then you reach the pole 90 degree. So the altitude is measured 0 to 90, and azimuth is measured from north to north again, 0, 90, 80, 270, and so on. This is how it is measured. Now, one thing is there, the horizon of every person at a different place will be different. Your horizon will be different in Ahmedabad. If you move to say Delhi, then the horizon will be different and so on. And that is the reason why when we had this eclipse recently in December, the view of the eclipse from Delhi was different, from here it was different, from south it was annular, right? So if, from every different place, because the horizon is different, you had a different view. So now comes a question, if the horizon is different from different place and the altitude and azimuth are different, then there will be an ambiguity. How would you tell a certain person that what will be visible based on your horizon coordinates? So it is a local coordinate system, and you need something universal which everybody can refer to, right? So we need another kind of coordinate system also. Fine. Now, after this, the direction part, we go to the how to find time and direction also. All title is Three Prashna Adhikar, Three Prashna. You must know answer to three questions before you can do any astronomy. And what are those three things? Location, that is place, direction, and time. Because direction, place, and time will decide what sky you will see. This was just an activity which we carried out 1.5 years back, and it you how to find out the altitude. You see, with this simple device, you can find the altitude, azimuth of sun. You can find the terms to the south direction. Naturally, this will be north. Right? This is east, and this is west. Initially, in the morning, the shape of the pencil will be very far away from the pencil, because tip of the pencil, because the altitude of the sun is low. And then as the sun rises, the shadow becomes smaller, 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 becomes minimum here when the sun is crossing the meridian, that is the north-south line. And then in the evening, it will go like this. So this is how the shadow will move during the whole day. With days passing on, this curve will become flatter and flatter, and then one day it will become a straight line, and then the curvature will go in the reverse direction like this. If this is calibrated, then we can find out the time also, and which was done historically. If you see, so various sundials will be there. You get a sundial out of this. So you can find the direction at daytime, the north, the geographic north, using this. At night time, you can find the geographic north by simply observing the pole star, where the pole star is. The direction of pole star is true north, and the altitude or the angle which the pole star makes, which with your horizon, will give you the latitude of your place. So this is how it can be done. Another, see, I will simply tell you how to find the altitude also. This is pencil. Okay, you put this pencil here and you are getting the shadow. This is exactly the north-south. You are talking about the meridian shadow. And if you join this, then this is somewhere where the sun is. And this is your zenith. This angle and this angle, so this is 90 degree. So naturally you can find this angle, and from this angle you can find out the latitude plus declination. This angle is actually the subtraction or addition of declination and the latitude. If you know the latitude, you can find the declination at that particular day. if you know the declination or the obliquity of the ecliptic, then you can find the latitude of your place. A simple one reading and a couple of steps will give you the latitude of your place like this. Okay. So this has been calibrated. This is a sundial, and of course, this angle will be equal to the latitude of your place. If you see this line as I was talking, this is in December, this is in June, and this straight line represents equinox. So a noon shadow, this is the noon shadow. In December, it will be here, and December to June, it will decrease like that, and it will be here, almost at the base of the triangle. And then in the next 6 months, it will again go this in this direction. So if you calibrate, you know in which month the sun is in which constellation. So if you calibrate this, see I have put this, this represents Taurus, this represents Aries. So from this sundial, you can not only find the time, but you can also tell in which zodiac constellation the sun is right now. So this is what can be done. Okay. Now, as I said, the sun shadow moves like this. Okay. So if you look at these three diagrams, the first diagram represents the sun on March 21 equinox. This is the daily path. This is the path on which it will rise and set. Now, gradually, as the days goes by, the sun moves gradually northwards, rises from here, sets from here, rises from here, sets from here, and so on. It moves like this. And eventually, in 3 months' time, June, it rises from this position and sets on this position. So now the sun is higher up in the sky. As you can see, it's almost zenith. If this is March, you can see the shadow here. This is the shadow, and now the shadow has gone. So this is what we call the zero shadow. These days, people are observing zero shadow day. A lot of school children and college students are doing lots of activity. They're observing the zero shadow. And then after June, again, the setting and rising position change. They reach here again in September, still move on. And in December, these are the two positions, the rise and set position. And as you can see now, the shadow is longest, right? So basically, you have this region where you have zero shadow, and you can actually experience that zero shadow. I'm showing you a small video where on the zero shadow time, I had put a glass, and as you can see, the shadow was not there. So this is when exactly the shadow goes, right? But this can be experienced only for people who are staying between 23.5 north latitude and 23.5 south latitude, because the sun is not going to go above, the declination will not go beyond 23.5, either north or south. So this one figure shows you the relative position of the sun rise and set in June and in December. Now, when in December the sun rises extreme southeast and sets extreme southwest, then that day onwards, it starts moving in this direction. So it rises on the eastern horizon, sets on the western horizon, but it starts gradually moving in the northward direction. And that is the reason why this December 21 or 22 is known as Uttarayan. The sun starts moving northwards that day onwards. Similarly, when it has gone this far, then from this day, that is June 22 or 21, it starts gradually while rising and setting towards the south, and that is known as the Dakshinayan. Now, when we talk about Uttarayan and Dakshinayan, one thing comes to mind. The most often asked question is regarding Makar Sankranti and Uttarayan, because even in newspapers it is mentioned that the holiday of January 14 is for Uttarayan. but actually it is not the case. Uttarayan, as I said, always happens on 21 December and it starts moving this. So Uttarayan does take place invariably 21 or 22nd December. So then why this mix up? Why was Uttarayan and Makar Sankranti mixed up and now it's different? So this figure will help you. This is a figure which tells you about around 285 AD. When, see, this is the Uttarayan position, the sun rises here and travels like this and sets here. But what are the star constellation which are behind the sun? The sun is in Capricorn. So in 285 AD, the sun was in Capricorn when it started moving northwards. And therefore, around 1500 to 1700 year back, Makar Sankranti and Uttarayan were on the same day, right? But now what has happened? If you look at the actual position these days, then you will find that on 21 December, it is in Dhanu Rashi, it is Sagittarius. So now what has happened? Some 1800 years back, when sun was setting here, the constellation was Capricorn, but now Sagittarius has moved in. So the whole ecliptic has changed, right? And similarly, now instead of Cancer here, this is Dakshinayan position. The sun rises here, sets here, but it is in Cancer. This was in 285 AD. Now, this group, Gemini, has moved in. If you want to understand this, you have to look at a other coordinate system other than the horizon coordinate system, that is altitude and azimuth. So this figure will help us. See, actually, this is not the actual position of sun and earth, but it simply helps you to show that this is the plane of the ecliptic. Ecliptic plane means a plane in which the earth is moving around the sun. So this is your ecliptic plane, and naturally this is the equator of earth. And if that is projected outwards on the celestial sphere, then this is earth's equator, this is the celestial equator, and this is the ecliptic. So you have two paths crossing each other, and the intersection point is known as the vernal equinox, the March equinox, the equinox which comes on March 21. And this is your first point of Aries, right? So in 285 AD, the first point was Aries was here on March 21. Fine. Now what happens? The pole, this is the North Pole. This is our Polaris. But the Earth axis has a other motion, and it traces a cone. It traces a cone. So what happens when the Earth's axis moves in this particular direction? This particular ecliptic plane, and this is the celestial equator. So when the Earth's pole, the axis traces a cone, then this curve moves in this particular direction. And so if vernal equinox is here, then gradually this point will come here because the equator is moving along with this, right? Then again, this point will come forward and so on. So if today, if this is the vernal equinox, then next year this will not be the first point of Aries, but the point will move here. Then next it will move here and so on. We know that the pole takes around 25,000 years, 26,000 years to make a complete that cone. And therefore, this motion is very small. Roughly in 72 years, it will trace 1 degree. So in order to understand that, we come to the ecliptic coordinates, that is lambda, the longitude of the sun and the longitude of the first point of Aries. And another, the other coordinate is beta, the latitude of sun. But it is so very small, we take the latitude of the sun, beta, as 0. So now this will help us. And if you want to understand the difference between Makar Sankranti and Uttarayan, you have to take help of the ecliptic coordinates. First, see this diagram. See, this is the first point of Aries. And this I'm talking about 285 AD. 285 AD. What was the situation? This was the starting point of Aries. This is 30 degrees Rashi, one Rashi or one constellation, that is Aries. Then 30 to 60, it is Taurus, 90, it is Gemini, and so on. And therefore, on this side, you have 270, which is the starting point of Capricorn, Makar. The sun was here in 285 AD. Again, go back to the figure. This is the Makar Rashi was here, 285 AD. Behind the sun, we had Makar. So on Uttarayan day, sun entered Makar Rashi. Now what has opened? This is what happens, as I showed you here in this particular figure. So if the first point of Aries is, say, here in 2019, then in 2020, it moves retrograde by 50 arc seconds. And in 72 years, it corresponds to 1 degree. In this whole 1800 years, from 285 AD to 2020, what has happened? This point here has now moved in this position, and that is roughly 24 degree. That is what we'll find mentioned as Einoush. Einoush means the difference between the sign and Niran. We'll talk about that later, perhaps, if we have time. So in 285 AD, this was our Aries constellation. This was the first point of Aries. Now our coordinate, origin of the coordinate system has moved here. So the first point of Aries is in Pisces. Mesh Arambh Meen Rashi Mache, right? Okay, so what has happened? See, all the coordinates are moving like this. So what happens to this? If this point comes here, this moves here by the same amount. Okay, so the sun, which used to be here at the first point of Makar Rashi, Capricorn, is now here in Sagittarius 2020. 2000 I have said, but it's 2020. So what happens now when this thing happens? December 21. Now we don't have Capricorn, but the sun is here, and it takes some few days to come here and enter. How many days? See, this is 24 degrees. So roughly 24 degrees will correspond to 24 days. And therefore, if you find out December 21 plus 24 days, then you will arrive at 14 January. And therefore, Uttarayan always starts at 22 December, but sun enters Makar Rashi, that is here on January 14. So Uttarayan is 22 December, but and this will move on. Eventually, we'll have 15 January, 16 January, and so on, right? So for understanding this, we need to understand longitude, and it helps us. So this figure simply tells you the story. The sun is here, and when the earth is here, December 21, behind the sun, you no longer have Capricorn, but it is Sagittarius. And only when you move into January, then it will enter Capricorn, right? So this is the difference between Makar Sankranti and Uttarayan. Okay. Next, let us look at what is RA and DEC. We have looked at two systems, the ecliptic coordinate system and the horizon coordinate system. Horizon coordinate system is local for your particular place. Ecliptic longitude, of course, you can always convert from horizontal coordinates to ecliptic to equatorial, fine. We come to the equatorial coordinate system, and the coordinates for the equatorial coordinate systems are RA, that is right ascension and declination. And based on this, we have 4 cardinal points defined, which we have already seen. This is March 21, vernal equinox. Equinox, equi means equal, nox means night. So equinox simply says that you will have equal night, equal day, all places. And when is that? It is defined as when the sun's RA and declination is 0R and 0 degree, that is vernal equinox. Now, if you look at this, in 3 months' time, this changes to 6, again 3 months time changes by 6, 12, 18, and then it again comes back here. So that is 24 hours or 0 hour, it is one and the same. So this is how RA changes. Now this is in hours, but 1 hour means corresponds to 15 degree. So 6 hours means 90 degree. And this is 180 degree and so on. And this is declination. This is declination north and this is negative. So this is declination south. So this is how the four coordinates, four cardinal points, the two solstice point and the two equinoxes are defined. This will help you understand what I've said. This is the Earth and this is Sun at vernal equinox. RA is 0, declination is 0, the Sun here. Then the Sun moves and in 3 months time, it comes here. 1 month or 2 hours corresponds to 30 degrees. So in 3 months, it comes here and the declination is 23.25 north and the RA is 6 hours or 90 degrees. Then in 3 months time, the Sun goes, of course, it is not shown here, it is beyond the Earth. And then again, it comes here. So it is December 21, 18 hours or 270 degrees. And now the declination is south. So declination north and south, see how you can understand. This is Earth, right? Now this is the equator of the Earth. And when the Sun's declination is 23.5 north, see where the sun rays fall vertically. This is latitude 23.5, Tropic of Cancer. And similarly, now, so it is above the equator. And when the sun goes from here to here, then the vertical rays fall here. This is below the equator. Okay, this is equator. This is Tropic of Cancer. This is Tropic of Capricorn, right? So this is how the RA and declination change. Now, see one star is plotted here, right? Sun is having declination 90. The star here is also shown to have declination 90 degree. What does it mean? See, once you know RA and declination of stars are given everywhere. You'll in books they are given, on websites you will find them. You will always find them in planetarium programs. You click on any star in a planetarium program, it will immediately show the RA, declination, and ecliptic coordinates also it will show, and so on. But when you know the declination of a star and RA of a star, without even looking at the planetarium program, you can tell when it will be visible. See, let us take an example. But before that, I will simply show you the coordinate system. I simply explain what are the coordinates, but this is how you can understand it in a better way. This is your North Pole, and this is south. This is the celestial equator. So this is the pole and this is the celestial equator. They are at 90 degree because the equator of the Earth and the pole, they are perpendicular. Same way, the pole of the celestial sphere and the celestial equator are at 90 degrees. Now what does, for simplicity, first I have taken the first point of Aries here. It is on the meridian. This is the meridian circle. This is your meridian circle. And gamma is here, the first point of Aries. What are the coordinates? The right ascension is mentioned here. It is 4 hours. 4 hour means 1 hour is 15 degrees, I have told you. So 4 hours is 60. So this angle will be 60 degree angle. And if it's 30 more, then it hits the horizon, fine. And the declination is measured with respect to the equator. So this is 27 degree north latitude, right? So this is how the coordinates of a star are given. I will show you an example of a star having negative declination. Again, this is your first point of Aries, right? So this is 2 hours. 2 hours corresponds to 60 degree. Angle between these two is 60 degree. and this is declination minus, or declination is south. So on this side, declination is north. On this side, the declination is south. Now I have separated your meridian and the first point of Aries. This is your first point of Aries, right? And this is the meridian. And here a star is shown and some another number is written, -1R. What is it? It is the R angle. See, this first point of Aries, and here, this is total 3, and this is 1. It means this is 2 hours. It simply tells you that the first point of Aries has passed the meridian, and it is 2 hours since it passed the meridian. And what about this? This star is, the angle is -1. So it tells you that it still has 1 hour to go before it will hit the meridian. And therefore, this and this distance is 3 hours, but it is 2 hours since gamma crossed the meridian, and this star has still 1 hour. So this is our angle. You can relate it, but this is how you can understand the coordinate. So if you want to specify in this coordinates, the RA and DEC or the equatorial coordinates, you simply could find out how much this angle is and how far north or how far south it is. If you buy a telescope, as I said earlier, you have telescopes coming with azimuth mount. So that is horizon coordinates, right? Altitude and azimuth. But if you want to do some photography, then you have to track your camera or move your telescope with the speed with which the stars are moving. And therefore, many telescopes come with the equatorial mount. So equatorial mount, you just find out where the pole is and fix that. So declination is fixed, and then only one coordinate has to be changed. Okay, so let us, I will tell you quickly one thing about this sun's RA and declination. And simply by finding the declination and RA of a star, what can you tell about it? You will find, let us take an example. Okay, this is our celestial sphere, and this is, say, west. This is east. Now, sun's RA is 0 hour in March, and on 21 June, it is 6 hours. Right? So if we have a star 6 hours, and suppose on June 21, I select this, the sunset time, the sun is setting, right? Now the star Ardra or Betelgeuse, it has RA of 5 hours 55 minutes, right? So this is 6 hours, and Ardra, it is 5 hours 55. So the RA is almost same, right? So if the RA is same, means its position in the sky is near the sun. And therefore, when the sun sets, Betelgeuse also sets. It is with the sun, right? And what about this? If the sun is here on 21 June, this is 6 hours. And if this is 6 hours, then this will be 12, this will be 18, and this will be 0 hours. If this sun is here, then this will be 18 hours. So if you have a star, say Vega or Abhijit, it's not exactly 18 hours, it is 18 hours 36 minutes. But I'm supposing that it is 18 hours, then that particular star will be here. So on June 21, a star with RA 6 hours will rise and set with the sun, whereas a star having RA 18 hours will be opposite exactly, because this is 90 degree and this is 270, right? 180 degrees here. So simply by reading the coordinates, you can tell where the position of the star will be with respect to the sun. But of course, this situation will change if it is not June 21, because on September 21, RA will be its RA will be on this much. So any star with 12 hours will be with the sun. let me tell you something about the displacement of the equinox date. So, Sarbhai, I have time, no?
Yes, sir. You can continue, sir.
Okay. So, I told you about equinox and solstice. The duration of the tropical year is this. So that is 365 days and this much. So that is roughly 6 hours, right? So if equinox today is say here, then 6 hours late, then next year 12 hours late, then 18 hours late, right? Every year after one common year, the season begins this much late. So the equinox will shift and it will go like this. And then next, after 3 common years, we have one more day. So it again comes back and it falls again here. So that is how the equinox fluctuates between March 21 and March 20, like this. Okay, you have a small variation here. You can see this going down, 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 and down. And that comes from here because this is equal to 1461 days. But if you look at the tropical year, the year when the seasons repeat, then that multiplied by 4 corresponds to this much. And therefore, the difference between these two will be minus 45 minutes. So there are two variations, one 6 hours and one minus 45 minutes after 4 years. So this is 6, 12, 18, and 24, and then this goes minus 45. So this is how it moves. And therefore, there is a fluctuation between March 20 and March 21. Okay, I will skip this part because I already explained. Next, I come to Moon. Moon is also known as Som or Nakshatrapati. It is our natural satellite. And this image was taken using a 8-inch telescope and a Canon 700D. Now, we know that the moon also moves in elliptical orbit. I'm telling about sun and moon because these are the first two objects which you will see and try to understand when you are new to astronomy. Some prominent star, constellations, planets, and of course sun and moon. So you know that moon moves around the earth in an elliptical orbit, and it is at because it is in elliptical orbit, sometimes it will be here very near perigee, and here this is known as apogee. This is this much. So naturally, what happens? The average size is this much average, right? And but because if it is here, it will appear big, and naturally here it will appear small. Okay, and the difference is this. This is the minimum distance and this is the maximum distance. So when it is at this distance, it appears small. When it is at this distance, it appears big. And the difference is 14%. And this is what you hear, that we have a super moon. It will be 14% bigger, it will be 30% brighter, and so on. Now let us look at our, this is the new moon position and we have a star here. What happens when the moon completes one rotation, that is again it is in the same position with respect to the stars, then that is known as a sidereal month. So that sidereal month is 27.32 days. But when it is completed, again it is not a, now it is here, right? Again the sun and moon both are at the same. So this is roughly 2 days. And therefore this is 29.53 days. So this is sidereal month, and this is synodic month. So the moon, if it is near a particular star, will again come back to the same star after 27.33 days. But face to face, that if it is at near a particular star and it is full moon, again it will come back near to that star after 27.33 days. But the phase will not be full. It will take 2 more days. And therefore, the phase repeat after 29.53 days. So these are the 2 months. This is how the phase changes. And this is our month. Our month is, right, this 30th is. So now look at this. You know the motion of sun. We also now know the position of moon and the phase of the moon. And the phase of the moon decides our month. And our months have 30 tithis, 15 Shukla Paksh tithis, 15 Vad Paksh tithis, and 29.53 days. For that equivalent, we have 30 tithis. Okay. Now, sun appears to move one complete circle around the earth. Actually, earth moves around the sun, but you see sun moving against the background of stars. So nothing wrong in it. In the 360-degree rotation in this manner, this is tropical year. So that is roughly approximately 1 degree per day the sun moves with respect to the stars. But moon moves 360 degrees in 27.33 days. This is the nakshatrik month or sidereal month. This is the sidereal month, right? So if you divide this number by this number, you get around 30 degrees per day, right? So the sun moves 1 degree per day. This moves 13 degree per day. And therefore, 13 minus 1 is equals to 12 degree difference or between the sun and the moon daily. This happens. I will tell you. See, this is the, suppose this is the moon, this is Earth, and the moon is here in Sagittarius. This is our zodiac belt. Okay, if the moon is here, then it will complete one rotation here in 27.33 days. Okay, so in 3 days time, it will come here, 40 degrees in 3 days. So that is 13 degrees and 14 degrees if you are comfortable with. And therefore what happens? The moon changes Rashi or constellation in 2.25 days. And this is what is the difference between Rashi and Nakshatra. This whole zodiac belt which we have, okay, this is one Rashi, 30 degrees. Okay, and we have 12 such. So then the question comes, why we have 12 zodiac constellation and not 15 or maybe 20 or maybe decimal 10? Okay, and why there are 27 nakshatra? Yet there are 27 nakshatra and 12 rasis. The reason is very simple. Moon phase makes our month. It is written in literature, Masa Kruth, maker of the month is moon, because it's a phase repeat after 29.53 days, right? So in roughly in 30 days, 1 month, okay? And it again comes back here. So in order to find out how much the sun moves when one cycle of the moon's phase change or repeat itself, you have to divide the sky by 12 in 12 different sections. So that is 30 degree section, 12 months. But then the another question is, you see daily the moon, right? And from one sunset to another sunset or one night to another night, how much the moon has moved. So naturally, because it moves and comes back here in 27 days, you divide the whole sky into 27 nakshatras. So this is how in the Indian system, we have the concept of nakshatra, where there are 27 nakshatra. The moon moves to a new nakshatra every day, and therefore it is known as nakshatrapati. Okay, so one part of the Panchang I already told you, because this is, we are studying the motion of the moon. And this is it. Okay, 27.30, 27 parts it is divided. So if the moon is, say, here today, Pisces, I hope you can see clearly the map. Next day, the moon changes the position from here and it comes in this position. Next day, it moves from this position to this Bharani, Krutika, and like that. So the moon moves initially from this position to this position, to this position, to this position, to this position. Now, actually, nakshatra is a angular angle or arc. So, if this is 13 degrees, that is one nakshatra. How do you find out an arc in the sky? So, if you have a bright star in that arc, then you identify that 13-degree arc with the help of a prominent star within it. So here it is identified with this. If in the next, this is next 13 degrees, then between this you have this prominent star. This is known as a Yoga Tara. This is Ashwini Tara. So this arc from here to here, it will be identified. This arc will be identified by this particular star. This is how the nakshatra is there. Phase I've already explained, and I was talking about Tithi, so let us see what is a Tithi. 12 degree separation, I've told you, is a Tithi. I will try to go a little quickly because it's already 16:37. Okay, so this is what happens. If you daily observe the sun and the moon, this is the setting sun, and the moon is setting along with the sun. This is Amavasya, or the new moon day. Next day, what happens? A 12 degree separation opens up between the sun and the moon. So it comes here. This is Sukla Pratipada. Then next, again 12 degree separation. So it is 2 days, and this is Sud Beach. Similarly, a 90 degree separation in 7 days, and 180 degree separation here in 15 days, because we know that 15 multiplied by 12 is equal to 180. So in 15 days time, at 12 degrees per day, from Amavasya, we have moon, and so on. This is how the Tithi goes. Fine. I will not go into this. Now let us talk about two planets a little bit. One outer planet, one inner planet, because this is what you observe. These days, Mars, Jupiter, Saturn, and Moon are visible in the morning sky. And sometimes you come across a newspaper item or that Mars is a retrograde. A graha is being vakri, right? So what happens? Suppose you have Mars here and you observe its position daily, then this is what you actually see. It is going in the forward direction like this. Then it starts its return journey. This is what you actually see in the sky. So this is Vakri or retrograde. And then again it has become prograde. It is going like this. Fine. So how do you explain this? All the planets move in orbits around the sun and no planet stops and comes back. So then why do you see a star going a planet going retrograde in the sky and then again going prograde? So this is Vakri and Margi, as we call it in Gujarati. You find it mentioned in a calendar. Now it is easy to understand this once we know the actual motion of the planets in the sky. Right? Again, I will play this so that you get an idea. It is prograde growing from Leo towards Virgo. Then you see it stop for a few days. Then you see it going back. And then this is retrograde or Vakri. And then again it becomes Margi, prograde. It goes like this. So how do you understand this? So this shows the orbit of Earth and Mars. Now naturally, a planet which is nearer to the sun will move faster. Mercury moves the fastest, and as you go from Jupiter to Saturn and so on, they move slower and slower. So what happens? Because of the orbits around the sun, a faster moving planet will always overtake the planet. As you can see here. See, we start from here, they are both here, and then more than 2 years time, what happens? The Earth overtakes because the Mars is moving slowly. So this is what you actually see in the sky. See, when the Earth overtakes here, the Earth overtakes Mars, then you see it going retrograde. And because the orbits are circular, they are not straight line, you again will find it when it goes beyond this point, you will find it again going prograde. So this is what you actually see in the sky. But concentrate here, Earth is going and Mars are going in the same direction. No planet is stopping and coming back, but this is what is actually happening, right? Next, I will simply touch upon Venus, and then I will stop. I think I have a few more minutes, 5-10 minutes, I suppose.
Yes, sir.
Okay. So Venus is very bright these days, and it's you can see it in the western sky. Many times you see it in the evenings, as in the morning also, morning sky. You never see it overhead. So it's known as a morning and evening star. So is the case with Mercury. And another important thing is you can see its phase change, and it changes so prominently that sometimes you will find it like a moon of say 3 days, 4 days, બીજ ત્રીજનો ચંદ્રમા હોય એ રીતે આપણને લાગે. So I will simply just tell you about this. See, Mercury and Venus can be maximum away from the sun by say 28 degree and 47 degrees. So this is 47 degree for Venus. Now it is this is a western horizon. So this figure corresponds to the evening view. So this is the eastern elongation. When the planet is Mercury or Venus are in eastern elongation, they are visible in the evening sky. When they are in the western elongation, they are visible in the morning sky. Now it is very simple to understand eastern elongation because this is the west horizon, and naturally towards this it is east. So Venus is eastwards compared to moon, I mean the sun, and therefore it is known as the eastern elongation. The angle for this is 28, and it is not difficult to understand why. See, the angle can never be beyond a particular. If this is the case of Mercury, the angle which is formed here will never be more than 28. And because Venus is outside the Mercury orbit, the angle is greater. So this is the sun, this is the earth. And when Venus moves on this path, then when it comes here, this angle is 90 degree. And when this is 90 degree, the phase is half, okay? And this angle is maximum 47. This is the evening star and eastern elongation. Here, this is a morning star, it is western elongation. Again, the same geometry. This is 90 degree and this is 47. Now I'll show you two animations. We'll simply tell you about the evening and morning positions. Then I will stop. Then we can have question and answer session. It's 4:45 already. Okay, let us look at this. First, concentrate here. See, this is Earth, and this yellow triangle is you, the observer, and this dotted line is the horizon. When the planet Venus and Earth are on this side of the orbit, then what happens? You see, first, who goes below the horizon? I mean, comes up below the from the horizon. See, this Venus, and then Sun comes above horizon. Again, see, now Venus is above the horizon, so it rises first, and then Sun comes above the horizon, so it rises later on. So this is why Venus comes up, then Sun, and the sky brightens, so then you don't see Venus. Now this is instead of these positions, when both the planets are on this side, see what happens. As the Earth rotates, it is Sun, okay, which goes, both are above horizon now. First Sun will go below the horizon, and then Venus will go. So in the evening sky, you will first see the sunset, and then you can see Venus. I think it's 5:45, 4:45. So we have 15 more minutes, and we can have question and answer sessions. Tushar bhai?
Yes, sir, we can.
Okay.
Yes, sir. So can we take question answers?
Yes.
Okay, sir. Mm, So we have so many questions. Yes. Mm,
What happened?
just a minute. Yes, so we have one question from Neil Vadodaria.
Mhm.
Yes, Neil.
Uh, Hello, am I
Yes,
audible?
yes, yes.
I can hear you.
Okay. So, sir, you talked about the equinoxes,
Yes.
that it changes between 20 and the 21st March
Right.
at every 4 years.
Right.
Then you discussed that there is a 45-minute difference
Right.
that leads to. So, why doesn't that difference add up with time and say it goes to 19 or 18 March after 20 or 25 years?
Yes. So if you look at this, are you able to see my? Can you see my screen?
Yes.
Okay. So let me again come back here. Yes. See what I told you that it goes because the seasons start late by almost 6 hours. So every year it will move by 6 hours. So first year it is year, then second year it's 12, 13, 18, and then 24. But then there is a 45 minute. Why there is a 45 minute? Because our 4 years are made up of 3 common years, 365 days, and the fourth one is 366. So that one day adds up and you are back there. But that days are 1461, whereas this, if you take 4 years of a season, tropical year, then it amounts to this 1460.96, and that is 45 minutes, and it goes up, adding up. But then why does it
So, what was the phenomena that we were able to observe it, and why only for a few months? Nowadays, only it is seen. So, what is the reason for that?
see international space station or in any satellite will have well-defined orbit and distance, and therefore it will not be always visible from a particular place. So there will be a period of a few days to a week or more when the satellite will not be visible from your geographic location. It will be visible from some other locations. So every few days that happens with the satellites via space station or any other satellite. It happens because of the orbital parameters. It does not always daily pass from your location.
Yes. We have a next question from Swati.
Mm.
Good evening, sir.
Good evening.
Hello.
I can hear you.
Sir, is it ever okay? Is it ever possible to go back in time of Ramayana and Mahabharat and calculate the weather conditions and other geographical factor of that particular time via calculations?
See, via calculations, you can find out the dates. If you have a manuscript where some positions of a star or maybe eclipses are the best thing. See, you will get many manuscripts where eclipses have been mentioned. Now,
Okay.
some sun, moon positions and eclipses are those things which you can always calculate for future also, and you can do backward calculation also. So when you go from, this was what I was talking, and our calendar, the calendar used in India traditionally was not, means it was in Nirayan, right? And I announce will help us to identify the date when those eclipses took place. right? So we can do back calculation for astronomical events or star positions or planet positions if they are mentioned. On those days, probably mean positions would have been given, but we can calculate. If we know the true positions, we can always calculate the mean position. As far as the geographic condition and weather condition is concerned, from astronomical calculation, it is not possible to find out the weather conditions. So this is something which geologists would be interested in. They must have some methods.
Yes, sir. Now we can take last question from
Yes.
Arshi Ali.
Okay,
Hello, sir.
fine. You can ask.
Okay, so is the pole star permanent?
No,
Um,
pole star is not permanent in the sense that I told you while explaining the ecliptic coordinate that our pole traces a cone, right? Our Earth is like a top, and just as the axis of the top traces a cone, the axis of the Earth is also tracing a cone. And right now it is pointing not exactly, but very near to the North Pole or the Polaris. So it is a pole star. But in future, we will lose Polaris as our pole star. And in some few thousand years, 12,000 years, Abhijit or Vega will become a pole star. And then it will repeat. So as I told you, in roughly 26,000 years, the axis of the Earth traces a cone, and whichever star is very near or in front of that axis, say, will become the pole star. So that is not a constant. It is Dhruv, but not Dhruv in a true sense. In the long run, it is not Dhruv.
Correct. Yes, sir. So I think it now, if anybody has the question, we can surely take through the Google Forms, and sir will answer that questions in
Okay,
that.
fine.
Now, yes. Now I would like to invite head of the department, Dr. Rajesh Iyer, sir, for the vote of thanks as well as for the concluding remarks of this webinar. Over to you, sir.
So,
Fine.
and thank you so much for such an illuminating lecture.
I'm also happy to interact with all the participants.
Yeah, it was, but so for some of us who are taking baby steps in the field of stargazing, the amount of information you gave us in terms of the astronomical thing, and finally you moved on to the astrological terms and tried to explain scientifically what they are. Beginning from why the skyline should look different at different geographical locations, and how the North Star and determining the latitude of a place, the sundial, the vernal equinox. It was the interesting facts about why the Makar Sankranti and Uttarayan have got drifted over the period of time. The nakshatra, the constellation, the tithi. So the different phases of Moon and Venus, these are all some of the things which many of us did not know it scientifically. And thank you so much. A different flavor is what we have got on all these 3 days. It's quite extraordinary that we began with what stars are and what they're made up of, and then we ended up with star gazing. I mean, two extremes. And in between the two, we had this information on planets, asteroids, meteors, and a whole lot of things which are offshoot of stars. And it has been terrific. And many of the participants were taking initial steps in the field of astronomy. These 3 days have been very informative. And I'm sure this is going to be creating a lot of interest amongst the students and science educators, and there's a wide cross section of audience which has been part of this webinar. And it has been terrific. And thank you once again, sir, for being part of this 3 lecture series. Thanks a lot. And we, as we have been constantly briefed, the amount of this thing you're passing on to the next generation, the passion with which you're pursuing. And we hope you would continue to do that with our students, and you've been doing it with so many other students too. Thank you so much once again.
Thank you so much, sir. Now, we would like to have one view from one of the students of the astronomy club, that what you gained and what they have gained in this 3 days. Very quick and very brief. I would like to invite Vaibhav Trivedi.
Hello, thank you, Chintan Bhai. Good afternoon, everyone. Sir, we learned so many new things and concepts about astronomy and astrophysics from this amazing webinar series. In first lecture, we learned a lot of about different star and HR diagram, which is the basis of astrophysics. In the second lecture, we understood the solar system, planets, comets, asteroid. Therefore, so many confusion got over from that. And from today's session, we learned to understand the sky above us. Therefore, we don't really need telescope to observe those. We just need calculation, and then we can get good results. This amazing webinar series provides new winds to our knowledge of astronomy and astrophysics. Thank you so much to all the speakers for motivating us during this lockdown period. And these type of webinars are so useful for the students like us. We get opportunity to learn something new by sitting at our home. Thank you, sir.
Yes, thank you, Vaibhav. Now, very quickly, I want to add something that two of our students from Astronomy Club, one is Jahan Thakkar and other is Christian Malavia. They both are the student ambassadors of International Astronomy and Astrophysics Competition 2020, IAAC. And now, on behalf of that, I would like to invite one of the participants, Jahan Thakkar, to quickly give some of the brief information and to give some information to the participants and the new astronomers. Please Jahan Thakkar.
Hello, am I audible?
Yes, you can start.
Thank you, Chintan Bhai. And first of all, I'll thank you, Professor Brijmohan and Thakore sir, for this wonderful talk. And we have learned so many things. Actually, what are the things we can do by just sitting at home in this specific period and do many creative things about astronomy and astrophysics. Now, I am also going to present such thing. Chintan Bhai, presentation.
Yes, yeah, Brijmohan sir, there is one request. Can you, sir, please stop sharing so that we can?
Oh, okay.
Thank you, sir.
Okay, sorry.
No, not problem at all, sir.
Yeah, so.
Yes, now I can see many of you.
Yes, sir. Yes, Jahan, continue.
Yeah, so I'm, as you can see, that's an international astronomy and astrophysics competition. This competition is specifically based on astronomy and astrophysics, and as you can see, it is international. So you can participate with a whole lot of world. First of all, what is IAAC? So it is a science competition, which is in which the problems will be given based on astronomy and astrophysics. There will be the 3 rounds, and one is qualification. The second one is pre-final round, and the third one is the final round. So this whole competition, the duration of this whole competition will be 2 months, and starting from the mid of the May to the end of the July, or probably the end of the July. There is a prize and certificates also there, and as you can see, it is there is no upper limit for participating. You can anyone who is over 10 years old can participate. So astronomy is our station, and this as I told, that the duration of this competition is 2 months, and it comes every year. So it is not only the competition. We can do many other things related to astronomy, astrophysics, like you can have lecture series or seminar and presentation, or astrofest collaborating with IAAC. As you can see, some photographs are there from all over the world. What are the benefits of this IAAC? First of all, it is online competition, total online competition. So in this period, you can participate it, obviously. And second, it is international. You have the global opportunity. The one other thing is it has spatial problems about scientific papers. It will come in the pre-final round. That there will be two research problems in which you have to study two papers based on astronomy or astrophysics or even cosmology, and there will be the questions based on that paper that you have to answer, and you will get a very wonderful experience in this competition. As I told you that there will be the 3 rounds. In qualification round is actually free. Everyone can participate with free of cost. There will be the 5 problems based on this knowledge calculation and somewhat research. Even that school problems, school students can also solve it. There will be very basic problems in qualification round. In pre-final rounds, there will be the 4 basic problems, 4 advanced problems, which is a bit higher. You will get some advanced knowledge in astrophysics to solve these questions. And I told you that there will be 2 research problems, which is the comprehension of research paper. In qualification round, you will have probably the 1 month time to upload your solution. Will be you can download the problems from the site, and then you write the solution, and then take the photograph, scan it, and upload to the site. This way you have to participate in final round. Final round, there will be a 40 multiple choice question, and you will have 60 minutes time, as we have in our many competitive exams. And there will also be the teacher supervision. So you have to select a teacher, and a teacher should be an authorized professor or teacher or from school or college, and he should also he has to also register as a teacher in that IAAC, so that he can supervise your final round. The prizes and awards will be, as you can see in the slide, that the first, second, third prize. Also, there will be regional awards that according to that continent-wise, or you can say like that. And all the participants will be given the participant certificate for each round. If you have only participated in qualification round, you will get the qualification round certificate. It is not like that you have to go until the end to get the certificate. This is the timeline. The deadline of qualification round is 15th May 2020. It was 17th April, but due to this COVID-19, they have to extend this deadline. The evaluation will last until the 25th May. Then you have to go for pre-final round registration. If you qualify the qualification round, you have to go for pre-final registration. There will be the fees, $8 fees for pre-final registration. Then you will have 1 week time for the pre-final round, and then the evaluation will last 29th June, and then the final round will come into picture, and the teacher registration and final exam should be taken until 17th July, and you will get the end of the competition is 20th July. So as I told, submission deadline is 15th May. In qualification round, you can work alone, or you can also solve problems in group also. You can scan the problems, scan the answers as your handwritten, or you can type it on computer and then scan the document. If you type it on computer, you will get the special honor in your certificate, because it is a special skill that you have achieved, so it should be appreciated. And you have to submit your answers on this given URL. And if you are under the 18 years, the cutoff for qualification for pre-final is 15 points from 25. As I told you, the five problems, each of with 5 points. And if you are over 18 years old, the cutoff will be 20 points. So here is the information about this different types of URLs and flyers and other. And below I have given my mail and of Kishan's mail. As Chintan Bhai told you, we are the ambassadors of official ambassadors of this competition. So anyone interested can mail us, and if any queries are there, we will definitely answer you. And here is our contact page. Thank you. Thank you for listening to me patiently. Thank you, Chintan bhai.
Thank you so much, Jahan. I think that's it for the today's session. Thank you, Brijmohan sir, for allowing to share this information in your session. Thank you so much, sir. And let me tell you, give brief information that you all have participated very enthusiastically in this webinar, and you all were more than 500, not only from India this time, 20 states and 5 union territories of India, but also you were from out of the India and the countries like Germany and Nepal. Thank you so much for actively participating in this webinar, and we thank you all. And once again, I would like to thank the senior professor, Dr. Tushar Pandya sir, and the head of the department, Dr. Rajesh Iyer sir, for the guidance and this initiative. We also thank Father Principal, Father Lancelot de Cruz, to give the permission and to allow us to conduct this event. Thank you all. Thank you so much.
Thank you very much to all of you.
Thank you all, and we look forward to participate in upcoming webinars. Thank you so much.
Once again, thanks to Professor Brijmohan sir. Thanks.
Thank you.
Thank you.
Thank you.
You can leave the meeting now, no problem.
Yes.